Hey,
Hello.
how's it going?
It's going all right. How about you?
Pretty good.
Good, good.
We finally have a break. I think I already, I'm ready for a big break, but it's only one day though.
Yeah. Someone described it as the first day of spring break. Like they took spring break's week and just chopped it up throughout the semester. So enjoy our first day of spring break, I suppose.
Yes, I think these people are insane. How do they expect people to be able to focus on Zoom?
Yeah. I agree.
With I don't know, that seems good. One day is nothing for me.
Yeah, I mean, I'm going to spend the day catching up on like grading and other stuff. It's not really a break, but it is what it
Yes, I
is.
think I will meet with Dino. So
Yeah.
at least somebody will have a break, right? I mean, some student will have a break. Yes.
Yeah. Yeah, exactly. Well, so pre-calculus has a test this Friday. So it's not really a break for them. They're probably gonna be stressing about the exam. So
And is it an in-person exam or is it a?
I'm doing mine through Zoom, but I know
Yeah.
some people are like kind of breaking their classes up into like an in-person and online for the first exam. So some people will take it in person, and then the second exam they'll switch. So
Yeah, so I actually have an in-person exam next week, and I think I figured out how to do this. I want to do it one day, not 2 days. But I'm going to ask Pete because he's teaching at the same time as me, but on the next room.
mm, hmm
So I have 203, and I think Pete has 204.
right,
So if I can take that room,
that'd be really cool.
yes, and then I can even ask Pete now.
What?
So do you actually go to class physically to teach? I mean, I need your room for one day, and I believe you teach at 10:20 linear algebra, I think.
No, it's 3100, but no, I don't use the.
So can I use it for next Wednesday at 10:20 then until 11:10?
It's fine with me. Yeah,
Okay, thanks.
sure. All right. Hope everyone had a good weekend. Yeah. So as I said, so today I want to. So we had like a long lecture. I guess I did an extra half hour or so on Friday that I uploaded, I believe, to the ELC. And so that took us most of the way through the preliminary results needed for the Tate-Nakayama lemma, which is this very specific non-trivial result in the cohomology of Tate cohomology of finite groups that when you plug it in the right way, gives you a big piece of class field theory. Yeah, so I had done a lot of the preliminaries. There's a couple more things, but the main, which I'll cover some of them. The last main ingredient by far, in order to appreciate the statement of the Tate-Nakayama lemma, is just the cup products in either ordinary group cohomology for an arbitrary group, or though I won't really say much about how you define it, Tate cohomology for a finite group. Okay, so that's the plan. I'll do a little, like one more page of let's see, one more page of results on cohomological triviality and that sort of stuff, and then we'll switch back to talk about cup products, and then the final bit of it is not going to be the most satisfying because I'm just going to skip. I'm going to skip most of the last few proofs that lead up to Tate Nakayama. I think they're less interesting than the ones that we've seen already. And anyway, I think we need to be skipping something in order to get where we say we want to go. Okay, so let me get started. What was the last thing we proved? We just proved it took a bit of time. So we proved the main result in section 3.1 of Harari's text. So it's this theorem, which again is kind of a mouthful. So yeah, so what is this doing? This is sort of saying that sort of homological triviality can be detected on CeLO-P subgroups, among other things, and in particular, it's enough to have, if you have a finite group acting on a G module, it's enough to have vanishing of Tate homology for 2 consecutive indices for the CeLO-P subgroups for all primes P, and then that will give you the homological triviality of the module. I remind you, for a G module where G is a finite group, homologically trivial means a priori, it means that all of the higher homology groups n greater than 0 vanish for all subgroups H of G when applied to that module. But in fact, part B of this result is precisely telling us that that's equivalent to an a priori stronger condition. Namely, if your cohomologic, if what I just said holds, not only do all the ordinary cohomology groups for n greater than 0 vanish, also all of the Tate cohomology groups for all integers vanish when n is a positive integer. The Tate cohomology group, of course, by definition, coincides with the ordinary cohomology group. The Tate H0 and Tate H minus 1 are slightly modified. Super H0 and sub H0, and then the negative H's are group homology. Okay, so that's certainly an important result about homological triviality. Okay, so yeah, so the next result, just a couple of things that would get used. Yeah, so I think they just kind of get more technical, as you can see. So this one is still seems kind of reasonable. So I have a finite group, I have a homologically trivial module, we just talked about that, and then I have a Z-flat, equivalently torsion-free G module, and then the tensor. So the tensor product of a homologically trivial G module with the Z torsion-free G module is again going to be homologically trivial. Another part of the previous theorem that I guess the statement was complicated enough, but it did come out in the proof that we proved a little bit more. If A is homologically trivial, if, as for any module over any ring, you write it as a quotient of a free ZG module, then it came out that the homological triviality of A implied that this sort of module of relations, whatever the kernel of this map is must be projective as a ZG module. Okay. And then by a previous lemma, I'll find that for you. I believe the lemma says that if you take a weakly projective module and tensor it with a torsion-free module, then you're still weakly projective. Let's find that. Oh, okay. If you take a projective module and you tensor it with anything, then you're weakly projective. Okay, so I didn't remember it. It's a good thing I flipped back. I didn't remember exactly right. So projective tensor anything is weakly projective. Weakly projective implies homologically trivial easily. So, okay. And so therefore, by that result, well, R and F are both, one of them is free, the other one's projective, so they're both projective. You tensor with B, they're weakly projective and hence homologically trivial. Right, so what's the point of B being Z flat? Well, by definition of flat, when you take a tensor product over Z, with B, you preserve the exactness of the sequence. And so therefore you have this guy, and again, what are we saying? We're saying these two guys are homologically trivial. And so if you take the long exact sequence in Tate homology, if two of them are homologically trivial, then the third one is going to be homologically trivial. Okay, so that one was also nice. And then I'll state one more lemma, and maybe you'll see why I'm not going to prove it. It's just they're just getting a bit more technical. The proof of it is not completely trivial, but it's not so interesting either. So, okay, so now I have a finite group. I have a homomorphism of G modules, and I suppose that for every prime number p, there's some integer np such that the induced map on, should probably be, all of this should be NP. The induced map on Tate Chromology, NP Tate Chromology, is surjective. Oh, now I see why I didn't put in the NP. All right, sorry. The induced map on Tate Chromology is surjective at NP, bijective on NP plus 1, and injective on NP plus 2. So that's a very technical hypothesis. And then it turns out that if B is moreover Z flat, then the induced maps here that you get in Tate Chromology, well, again, I just have a map from A prime to A, and so then if I tensor this map with B, then I get a F tensor B map from A tensor B to A, from A prime tensor B to A tensor B, and then by the functoriality of group cohomology in the module, that gives me these maps. And it turns out that these maps are isomorphisms for all subgroups H of G and all N. So it's getting too technical, right? So again, the proof is certainly in the textbook, and I'll leave you to it. I guess maybe I'll flip ahead a little bit so you'll see what we do after we have a few pages of cup products. Yeah, so this is kind of the next result. Again, they're getting, yeah, well, maybe this is just scaring you at this point, but let's see, is it actually helpful to talk about this at the moment? No. Well, I guess the only thing that you need to see at the moment is that we have a very specific setup. Well, I'll come back to this later, don't worry, but we are taking the cup product with something in this proposition. Anyway, that's A sub H, whatever that is, cup something. So this map is a cup product map, and this map is some induced map. And so you see that, I guess the only point I'm making right now is that I've gone absolutely as far as I can go in chapter 3 without introducing the cup product, because the very next result is this like kind of technical looking result involving cup products. I'm only doing part of the proof. And then the very next result is the Tate-Nakayama theorem, which says if you have some very special cohomology class, then cupping with it is going to be an isomorphism. Okay, so I think it must be time to talk about cup products, right? We have nothing else to do right now except to talk about cup products. And well, you know, if I just give you a basic discussion, it's not so bad. I'm not going to be proving too much. Harari has a more careful than usual discussion of cup products. Okay, so it's good reference, I think. Okay, so the cup product is easy to define even at the cochain level, so that's good news. It's on the homogeneous cochain complex, which is the first cochain complex we introduced, and then via just an isomorphism of modules, we were able to rewrite our kind of standard resolution in a way that kind of eliminated one of the variables, right? So the homogeneous cochains are the ones that are maps from, so the nth homogeneous, the nth element of the homogeneous cochain complex from G can be an arbitrary group right now into a G module A. Remember, these are maps that go from n+1 copies of G into A, right? Whereas and they're G equivariant, right? And then again, just as a very brief recall, the G equivariant, it's clear that G to the n+1 is a free G set. And so that gives you, if you take the G equivariance into account, as we did, you can remove one of the degrees of freedom. You can just, literally, you can just take this thing and evaluate the first coordinate at 1, and that gives you, losing no information, that kind of precisely uses up the G equivariance. And that's why the inhomogeneous cochains were maps from n copies of G into A. Okay, so sometimes the homogeneous cochains are useful And here's why. So the cup product is defined in a very reasonable looking way. So the cup product on cochains, I guess I forgot to calligraphy these K's, but they're supposed to be. So yeah, so it's a Z bilinear map from KP. Okay, I have two modules. So maybe one thing to call your attention to is that there's two kind of formal features here. I take as an input a P cochain and a Q cochain, and then the output is a P plus Q cochain. Okay, so that's what you would expect, I think, if, for instance, the cup product in singular cohomology works like that. And then the other thing that's happening is I take as input two different modules here, and then the output comes out into the tensor product. As ever, this is the tensor product over Z, if I don't say otherwise. Okay. And it's really, I mean, you can't argue with this nice simple formula. So the cup product, if it is such a thing, then, you know, it should take as input a P plus Q plus 1 tuple of elements of G, so starting at 0 and ending at P plus Q, and should output some element of A tensor B that takes into account what the A and the B were. And so A goes from 0 up to P, that's a P plus 1 tuple. B goes from P up to P plus Q, that's a Q plus 1 tuple. Note that the GP is being fed in as input to both the A and the B there, and that's your definition. Okay, so like, this is what's nice about cohomology rather than homology. It actually makes sense to, I mean, in some sense, we're just formally multiplying them using the tensor products. And then I have to confess, it's been way too long since I thought about cup products in singular cohomology, at least 20 years. As I started thinking of that, I feared that I may never have given the super close attention to the definition of the cup product in singular cohomology that it deserves. But so you guys can tell me, or we can both look at it in our leisure. But I suspect this is actually rather similar to how the cup product is defined in in actual topological. I mean, there might be something that you're in topological cohomology, you might have been expecting maybe you like coefficient rings better than coefficient groups. And so you might have expected, well, what if I just put a Z? If I put a Z here and a Z here, I should be able to get a Z out here, right? And so in particular, the cup product is giving a ring structure to the, let's just say the singular cohomology, right? And that's happening here. So that there will be a little coming up very soon. There'll be a short discussion on there's a cup products play nicely with bilinear pairings, and so that there's a discussion of that. So that'll come up. Okay. So right. So here's the most basic result. Okay. So I'm not going to prove just this very reasonable looking, this is like some kind of graded version of the Leibniz rule, I guess, right? So if I have a P cochain and a Q cochain, and I'm trying to understand like how the boundary operator interacts with the cup product, right? And so if I didn't have this -1 to the P here, so if P was even, then like this would really look like a derivation, or like a Leibniz rule, type thing. And as usual, when you're doing graded stuff, you kind of expect to see, your standard rules kind of twisted by -1 to something, right? So this is a very reasonable looking identity. I'm sure that some mathematicians would explain, there's a whole branch of mathematics, right, between like topology and algebra and algebraic topology. Robert Barlow is very into this, which discusses like differential graded algebras, right? So it's not exactly my thing, but this looks like a very reasonable identity. Okay, so I'm not going to prove the identity. The proof is on is in Harari. I will deduce the consequences of the identity. So very important consequences. If A and B are both cocycles, so by definition, that means that the what do you call it? The differential of them is equal to 0, then the cup product is also a cocycle. Okay, that's visually clear. I guess I'll say a little bit. The only thing that you need to see, well, if D of A is 0, then what's the point? The point is that is that the cup product is coming out as a tensor, and 0 tensor anything is 0. That's the only thing that's coming out of it. And with that comment, it's kind of clear that that's true. And then moreover, if one of AB is a cocycle and the other one is a coboundary, so I'll do the case where dA is equal to 0 and B is D of something else, then I claim that A cup B is D of something else. Okay, and that's so easy that I'll prove it. Okay, so let's see. Right, so for part A, see the textbook. For part B, as I said, it's visually clear once you allow yourself to believe that, so something cup 0 is going to be 0 because something tensor 0 is going to be 0. So how about part C? In theory, I should do it both ways around, but I'm about to give you a commutativity property of the cup product later on, and anyway, it works very similarly the other way. So suppose D of A is 0 and there's some element capital B whose differential is little b. Well, I did the 2 minutes of work myself, and I'm pretty sure that D of -1 to the P all times A cup capital B. The D is a z-linear map, so I can pull the -1 to the P out. Fine. I take that one. I have this graded Leibniz rule that I just didn't prove. Right, so that's D of A cup capital B plus another -1 to the P, A cup capital DB. Well, capital B was chosen so that DB is equal to B. DA is 0. 0 cup 0 is 0. That term goes away. Good thing I put in an extra -1 to the P. So I get A cup DB, which is A cup little b. Okay, well, I picked a pretty easy one to actually verify. Okay, but so what this has a very, very important consequence. So this means that the cup product is defined at the cochain level, but because of all this, it descends to a pairing on the cohomology. Okay, so it makes sense if you want to do it at the cochain level and do kernel non-image, then you're good. Okay, so I'll let you. It's simple. I'll certainly let you think about the fact that it follows, but it definitely does follow. So passing to cohomology, again, for now, G is a totally arbitrary group, and so P and Q are non-negative. And so we get a Z bilinear map of exactly the form that we just discussed. Okay, so it's going from any cohomology group of one module cross any ordinary Cartesian product here, any cohomology group of another module into the P plus Qth cohomology group of the tensor product. Okay, so that's the type of map that the cup product is. Okay, so just a couple special cases. If P is equal to 0, then I know then the 0th cohomology is the invariance. Okay, and so that looks like a simpler map. So in other words, for every element A of AG, you have to give me a map from HQ of GB to HQ of GA tensor B. So if you think about it, it would be sufficient if I gave you just a G module map from B into A tensor B, and then just by the functoriality of cohomology, that would induce a morphism on the cohomology. And sure, if you give me an element of AG, then I can just tensor with that element, and that will give me a G module map from B into A tensor B. So in the case where one of the indices is equal to 0, it's pretty darn clear what the cup product is. It's just the induced map on cohomology of tensoring with one of the factors. Okay. And then it's even more clear what the map is if both of the indices are equal to 0, right? So then I'm looking for some Z bilinear map from the G invariance of A cross the G invariance of B into the G invariance of A tensor B. If I had covered this up, there's only one guess, right? I take an A and a B, and where should I send them? I should probably send it to A tensor B, and of course the G action here is the diagonal action. So sure, if A is G invariant and B is G invariant, then G acts on it as GA, which is equal to A, tensor GB, which is equal to B. So no problem. This is a perfectly good Z bilinear map Z modules, okay? And then other people might want to try to take a much fancier approach and kind of go backwards and define the entire cup product by starting with this map and doing some kind of funny shifting, okay? It is possible to do something like that. There is like a more fancy, there's a fancier definition of the cup product map in Chromology where you don't actually say what it is on P cochains, cross Q cochains. You only say what it is on 0 cochains. I don't like that. Okay, there's a part of me which is like, oh, how elegant that you don't have to dirty yourself with cochains. But at some point, you're going to want to know if you're ever going to calculate anything with a cup product or even, think about it. It would be better to have, if there is some simple expression on cochains, then you want to know. And so, by the way, for instance, this is probably my least favorite part of Sarah's entire GTM local fields. Okay, so again, in the large, if you flip back, we are still following Sarah's local fields. Chapter 7, I just close my eyes, I can see it after all these years. So chapter 7, basic group Chromology, inflation, restriction, co-restriction, blah, blah, blah. Weekly projective, weekly injective. Chapter 8, Tate Chromology. Chapter 9, Tate Nakayama. Okay, so that's been the script for a while, but his discussion of cup products in his book does not, as I recall, actually tell you what it is at the cochain level. And it's like, well, why don't you tell me what it is at the cochain level? So not helpful. Okay, so here's the thing. There's the cup products interact very well with pairings in a very simple way. So if you have what's the right structure here? So I want A, B, and C all to be G modules, okay? And then I want phi to be a Z bilinear G module map. So I guess I'll pause for a second while you digest that, but it's exactly what it sounds like. Okay. Well, because it's a Z bilinear map, it factors through the tensor product, that the tensor product is universal for Z bilinear maps into a Z module. And I guess we should check that, that this factorization map, I guess that both of these factorization maps are actually G homomorphisms. It's completely clear that, I guess I did the easier one. It's completely clear that this map is a G homomorphism, as I said, because to say that this is a G homomorphism is like, tell me what the G action is on the tensor product. It's the G action that kind of makes it into a G homomorphism, I suppose. And then, as I just only now did I realize that I should also argue that this one is a G homomorphism, but I promise you that it is. Okay, so right, and so if you have a Z bilinear map, then in the category of G modules, it will factor through the tensor product. So what? Therefore, if you really didn't want your cup product to take values in the tensor product, and sometimes you don't, you want it to be a little simpler. As long as you have your Z bilinear pairing between A, B, and C, well, you take your cup products, and then this map here, I guess I should label it. This definitely depends upon the choice of phi. Phi could be 0, and this would be the 0 map. So this is precisely the map on P plus Qth cohomology induced by phi. Okay, so that's the point. This is a really nice way to look at this. So if you have a pairing, a priori the cup product lands in the tensor product of the two guys, but if you have a pairing from those two guys into a third thing, then you take the tensor product and compose with you do the module side functoriality, and you get a map into whatever A and B are paired into. Okay, so that's very important. I'll say a little bit more about this. It'll come up, I think, literally on the next page. But for instance, if A, B, and C are all equal to a ring R, then we're going to get a ring structure on the cohomology out of this, okay, which as we should, I suppose. Okay, so here's the part where I'm totally bailing out on. At the level of detail that we're giving at the course, I think it's it's just it's a bit technical, and you have to watch somebody else doing it, I guess, or watch somebody else doing it and then spend more time figuring out what's actually going on. But so I claim, because Tate claimed, that if G is finite, then the cup product extends to Tate cohomology in a canonical way. Okay. So in particular, Harari says, enumerates a certain list of properties that the cup product has on Tate cohomology, and then he says it's the unique map that has all those properties. And I don't even think I'm going to list all the properties, so I'm not going to make the uniqueness statement. But yeah, so I'm not even giving you the definition here. Notice it's good that there's a textbook you can check, but formally it behaves exactly the same. Yeah. Okay. I mean, maybe. I guess I did the two things at once. I mean, okay. The second thing generalizes the first thing. The map from A cross B into A tensor B is certainly a bilinear pairing. So I'm losing out on nothing by doing that. But yeah, so you also, if the group is finite, you also have the cup product defined on Tate cohomology for all indices. Okay. All right. So some properties of the cup product, and so the convention here is that all of these properties that I'm going to talk about, they either hold for the Tate cohomology, so all integer indices when G is finite, and they will also hold for, if G is infinite, they'll also hold, of course, as long as you take n to be a non-negative integer. But I think, yeah, in most cases, I mean, the case that we want is when G is a finite group, and we're taking Tate cohomology, so I don't want to write it twice, so I'll write, if I have to write something, I'll write Tate cohomology. Okay. So this first one is extremely important. Once you identify, so the tensor product is essentially is associative up to canonical isomorphism, so good enough. So once you identify this triple tensor product with that triple tensor product, then you can ask whether the cup product is associative. And thank goodness it is. Okay, so that's just a very, very basic and important fact. Okay, so I'm writing it down in Tate cohomology. Or, again, if it was an infinite group, the cup product would be associative in the usual cohomology, right? And so again, here's right. So for any ring R, I'm pretty sure. I mean, this is really not my area of expertise, but I really don't think the ring R needs to be commutative. I think, in fact, that for any ring, commutative or not, multiplication in that ring is a R bilinear map. Sorry, a Z bilinear map from R cross R to R. So this map is literally, multiplication in the ring. And so just, the fact that multiplication distributes over addition is basically telling me that it's a Z bilinear map. And so, yeah, so for any ring whatsoever, I think, commutative or otherwise, I don't care to do it for a non-commutative ring, whatever. You're gonna get two different cohomology rings here, by the way. So if the group G is totally arbitrary, you can take, again, if the group is infinite, then you only have, of course, these cohomology groups for n greater than or equal to 0, and so you take the direct sum of them, okay? And so I'm getting a graded algebra. Okay, I think I'm probably okay. Here's where I get nervous about R algebras. Okay, whatever. I don't think the ring has to be commutative, but I don't need the ring to be non-commutative. So if the ring is commutative, then both of these guys are going to be graded R algebras. Okay. I think there was some exercise about that if your module, if you have a commutative ring and you have a RG module rather than a ZG module, then you take cohomology, and the cohomology still retains the R module structure, just because everything that you do to get the cohomology, like the kernel and the image and all that. Everything in sight has an R module structure. The cochain complex has an R module structure. Okay. And so for any group whatsoever in any, let's say, commutative ring, you do this and you get a graded R algebra, which is your cohomology ring of that group. If the group is finite, you could still do that, or you could do more and you could take the Tate cohomology groups, and then this will give you this like Tate cohomology ring. Okay. And again, it's not what I do, but I claim that people who are interested, very, very interested in representation theory, are really do study these cohomology rings. So like literally just for an honest finite group, like if you're if you're a group theorist and you're studying your finite group, then the integral cohomology ring of that group is a very interesting invariant of the group. I think it's been a long time, but I think there's certain like online repositories of information about finite groups, right? It's just like go and you find various data about character tables and conjugacy classes and all that sort of thing. And so in some of these online repositories, they'll also give you like generators and relations for the cohomology rings of the group. So anyway, I'll just give you one example. And if you ask any questions about this example, I'll refer you to other people rather than myself. But yeah, so these rings are of great interest to group and representation theorists, even when R is a field. And so I want to refer you to a recent paper, Finite Generation of Tate Cohomology, by John Carlson, retired emeritus UGA professor, Sunil Chebelu, Jan Ninach. These are well-known algebraists. 2011 paper. And so they take a finite group G, they take a field K of positive characteristic. We like positive characteristic representation theory around here, which is harder. We take a finitely generated KG module, okay? And then it's kind of easy to convince yourself that if I took a ring, I would get a ring. But if I just take a module, then now by H star, I really mean like the direct sum over Z of HN hat GM, okay? So it's pretty easy to convince yourself that the direct sum of the H hat GNs are a graded module over this graded algebra. Everything acts on everything in the right way. And so if you start with a finitely generated KG module, then its total Tate cohomology naturally becomes a graded module over the cohomology ring with coefficients in the field K. And you can ask whether when this module is, so you started with a finitely generated module, you took Tate cohomology, then you ask whether the cohomology module remains finitely generated over the cohomology ring. And so there's a paper on this, and the answer is related to something called the support varieties of the module in the field. And maybe I'll go so far as to admit that I'm not super clear on what a support variety is, but I've certainly heard people like Daniel Nakano talk about it a lot over the years. Okay, so we're doing modern representation theory of finite groups here. Okay. I mean, it's some kind of algebraic variety over K that you attach to the module. Okay. All right, what else? I told you about the associativity. You can also identify again, by the way, I just remind you, things would be more complicated for an arbitrary commutative ring. We are using the fact that a group ring is canonically isomorphic to its opposite ring, which allows you to move around between left modules and right modules. Otherwise you would have, it would in fact be more complicated. And then again, you have this basic identity, which is I think what you would expect if I told you that I had a graded ring and I was wondering about the commutativity properties of the ring, like, isn't this what you wanted to see? I think it's what you would want to see. I think Harari, maybe I'm wrong, but Harari uses the term anti-commutative. That kind of doesn't sound right to me. Anti-commutative should mean that like there's always a minus sign. I think this is like graded commutative. Anyway, but it's a nice, it's like as close to commutativity as you should expect from a graded algebra. Okay. So, right, so the Tate homology has a nice ring structure. That's not where we're going, by the way. We're not going to make use of these homology rings. Okay, other properties. Let's see. Here again, I'm writing, just to write something, I'm writing Tate homology, and so therefore G should be finite. If I didn't want to do a Tate homology for an arbitrary group, I'm pretty sure that H could be any subgroup here whatsoever. It doesn't even have to be finite index. Anyway, cup product commutes with restriction. That's all that this identity is saying, so how nice. Now we're going to get also cup product commutes with inflation in a reasonable sense. And this is the reasonable sense. Okay, so cup product commutes with inflation. Great. Right, okay, so now to do co-restriction makes sense for infinite groups, but it's a kind of norm map. So like for sure you want a finite index subgroup because you're on the 0 level of co-restriction, you're summing over cosets, coset representatives. And so, yeah, so this is, yeah, okay, so that is the co-restriction. Does that look right? Let me just check to make sure that this looks reasonable. Maybe let me look this up for a second, actually. Make sure I wrote down the right thing. Yep. Yeah, I guess maybe for this it's helpful to I mean, I think it kind of has to be what I'm about to write down for it to make sense, but maybe it helps to see that alpha is in the Tate homology of H and beta is in the Tate homology of G. Sure. Same module. Okay, so that. Okay, right. Just look at that for a second. Oh, looks good. Okay, I mean, makes scans anyway. Okay, and so yeah, so for the proofs of these facts, you can see Harari, section 2.5 and section 2.6. And not only am I not telling you the proofs of the facts, I'm not even telling you all the facts. So he has some more nice compatibilities. In particular, I'm bailing out on the end of the proof of Tate Nakayama because the proof of the last technical statement before Tate Nakayama uses a compatibility property of the cup product that I just too much, like enough exposure at once. And so there's another property of the cup product that I haven't told you about that you can read about. Okay, so now so now we just have to turn the corner and finish our discussion of Tate Nakayama. Yeah, okay. So let's see, it's getting a little more technical now. So I have a bilinear pairing among G modules, so that hopefully that looks more reasonable than it did 20 minutes ago. Now we fix a Tate homology class. So A is just any old Tate homology class in some dimension for A. By AH, we mean the restriction of A to some subgroup H. D is some other G module, and so then now I'm defining this relatively complicated map, but this map is essentially, it is the cup product map. Well, there's a couple things going on. It's cupping with AH, okay, so we're restricting to the subgroup H, then we're cupping with AH, okay, and so if we do that, well, this guy was AH was in H hat Q H A. Okay, great. So we cup that with B tensor D, and so we tensor, tensor, tensor. So I get, I do indeed get Hn n plus Q, A tensor B tensor D, but then I have a bilinear pairing from A tensor B into C, so I can use that to kind of, you know, do one of these multiplications. And so of course there is a pairing from, a G module map from A tensor B tensor D into C tensor D. I just wrote that down. So you take A tensor B tensor D to phi of AB tensor D. Okay. So it's just getting a little messy. Anyway, so that's what this map is. Okay. And now this is, yeah, it's not the most inspiring result in the world. We suppose that for all prime numbers P, there exists some integer depending upon P, so that this horizontal induced map is surjective for n equals np, bijective for n equals np plus 1, injective for n equals np plus 2, which of course was the hypothesis of this last result, whose proof I decided to skip. Yeah, so here surely this lemma was going to be used. Okay. Oh yeah, what was the conclusion of the lemma? Yeah, so the conclusion of the lemma is that some induced map on Tate homology is an isomorphism. Okay, and the conclusion here is that for all subgroups and all torsion-free G modules, Z torsion-free, G modules D, then this map, I don't know why we said it, I think I'm probably following Harari, we said it was an isomorphism, now we're saying it's a bijection, those would mean the same thing, but let's use the same. Okay. All right. It's true, a bijective homomorphism of Z modules is an isomorphism, okay. All right, and so this is not very satisfying, but let me just do the Q equals 0 case so that we see what's happening. So I'm going to assume that this A is actually a 0th Tate homology class, which would be the easiest case because the 0th Tate homology is just the coinvariance modulo of the norm map. And so, if I have an element in the quotient, I'll lift it to some actually invariant element, and then let's see. So right, so I have F takes B to C. What's happening here? Right, in this case is just a G homomorphism given by, I define. Yeah, so I define the G homomorphism that you get. I mean, nothing is happening here. To say that I have a bilinear pairing means that for every element of A, I use that element of A and I get a homomorphism from B to C. And so that's what I'm doing. And then in this case, because of what I told you about what the cup product is, cupping with something which is in 0 cohomology, in this case, the cup product is just the induced map on cohomology. Okay. And so therefore, this map is the induced map on cohomology by our pairing tensor 1. And again, it's if you go back and you look back at the previous proposition or the previous lemma, the thing that I just flipped back and showed you. Again, it's just getting, it's not super hard, it's just getting technical, I think. Anyway, so this lemma said that if certain hypotheses that were satisfied, which was exactly, and okay, I'll flip back one more time. Anyway, so you can see, I mean, I think in this case, it's pretty clear. Z flat is the same as Z torsion free. Yeah, so it's pretty clear that at the Q equals 0 level, kind of nothing else is happening other than plugging in this last lemma, okay, whose proof I omitted, but wasn't so bad. And then, yeah, and so that was the Q equals 0 case. The general case is handled by some kind of shifting argument. Again, though, just because I say shifting, it might be routine, it might not be. This shifting argument cannot be completely routine because it is using a further compatibility of the property of the cup product that I haven't told you about. Okay, so sorry, this is meant to last a certain length of time rather than be super satisfying as an exposition, but what I'm omitting is just the most technical stuff. Okay, so that's the proposition. And now we're ready for the Tate-Nakayama lemma, and hopefully we can at least understand the statement of the Tate-Nakayama lemma. Okay, so the Tate-Nakayama lemma is like theorem. Yeah, let's call it a theorem. Somebody calls it a lemma. It has a lemma-like look to it. It's very specific. So I have a G module. G is finite. I have an element of the second cohomology, so that's very specific. And then I have these two very specific hypotheses. I assume that for all primes, the first cohomology vanishes when I restrict to every CeLO P subgroup. So as we've been doing, all our hypotheses are coming out in terms of the CeLO subgroups. And then we assume something even more specific, that if I restrict to this, if I look at the second cohomology restricted to a CeLO P subgroup, it is non-vanishing. Its size, as long as the CeLO P subgroup is non-vanishing, its size is precisely the CeLO P subgroup itself. Okay, so this is like, whoa, this is very specific. And moreover, so I have some group of order, whatever the size of the CeLO P subgroup is, some commutative cohomology group, and I don't even just want to assume that it has the right size. I had an element here that I haven't used yet, right? This cohomology class, and I want this cohomology group to be generated by the restriction of this element. Okay, so it's like somebody probably has some specific context in mind for this result, right? Otherwise, like, what in the world, right? Okay, and then the conclusion is for all torsion-free G modules and all subgroups and all indices, cupping with this magic Tate-Nakayama class will give you an isomorphism. Okay, so that's the result. And in particular, if even applying this when D is equal to Z, Z is a Z torsion-free G module. So if you apply it with D equals Z, then it's already, it's specific, but it's interesting. It's telling us that all of the Tate cohomology groups of Z are naturally isomorphic with this dimension shift by 2 to all of the Tate cohomology groups of A. Okay, so it's like we have this magic G module and we have this magic class. Okay, and cupping with this class is giving us, it's not. I'm not claiming that this is like a fundamental class like in Poincare duality or anything like that, but it has that kind of feel to it. There's like some very specific cohomology class we're hypothesizing that cupping with this cohomology class is giving us some isomorphisms. Okay, so the proof is kind of nothing. Nothing left. So what's the proof? I apply this very technical proposition with B equals Z, the integers, C equals A, Q equals 2. I guess we better flip back. A lot of stuff here. So B equals Z, C equals A. So now I have a bilinear pairing from A cross Z to A. If you think about it, if you have a Z module, then you always have the Z module structure on a Z module is given by a pairing from A cross Z into A. So I know what I want my pairing from A cross Z into A is. It's the one that gives me the Z module structure, namely how do I pair A and N together? I multiply A by N. Okay. So that's a lot of stuff is collapsing. What is this integer NP that is supposed to exist and have these properties in the proposition? So I need this this homomorphism induced by the cup product followed by the pairing to be surjective, then bijective, then injective. So let's try that out. So y is cupping, I'm going to do that with NP equals -1. So first of all, y is cupping with AP, surjective on the -1. Take homology. Well, it is because the second guy is equal to 0. That was one of our hypotheses. Okay, so you can't argue with that. If this guy is mapping into 0, then it's surjective. Okay, fine. The next level up, if I go from H0 into H, that's a 2. H2, that's supposed to be a bijection. Well, what is H0? This is Tate H0 of trivial Z structure. So it's the invariance, which is Z modulo the norm. Well, it's just action by the order of the group. So the Tate H0 for a finite group acting on Z is just Z modulo the order of the group. That's MP, the order of the CeLO P subgroup of G. Okay, so we have this induced map, and again, this is like what I told you before. If you're cupping with something at level 0, then basically you're just tensoring with something and taking the induced map in Chromology. So yeah, so once we identify everything correctly, I claim that this map really is just the map. I mean, I'm kind of just tensoring with whatever. I claim that once you unpack all this, you find I have a map from a cyclic group of not just any cyclic group of order M, literally Z mod MPZ. So I have a canonical element here. And where is that canonical element here going? Well, trust me that when you make these identifications and understand the simple recipe for cupping with something on a 0 cohomology group, right? Then the canonical generator 1 actually does go to this element AP. All right, cupping with AP takes 1 to AP. That sounds pretty reasonable. How do I multiply AP by 1? Yeah, you get AP. Right? Probably believe me. And so, okay, and so therefore this map is taking me from a cyclic group of order. Anyway, this map therefore must be a bijection because I've assumed that it is basically, right? So this group has order MP. This group apparently also has order MP, and this group apparently is generated by whatever. Obviously, I mean, I couldn't have rigged it more for this map to be a bijection, right? So this the fact that this map is a bijection is kind of a restatement of the second property. Okay, and then finally, when I go up one more dimension, I need that cupping with HP on the H1, going from H1 to H3 is supposed to be injective. So what fancy fact are we going to use for that? Well, okay, you can put a hat on it if you want. It's just the ordinary H1. Z as ever has the trivial GP action. So it's just hum from a finite group into a torsion-free group. Nope, that's 0, right? This would have to go to an element of finite order of which Z has none. Okay. So this map is in, so it's like this map is surjective for the easiest possible reason because the codomain is 0. This map is bijective because that's kind of exactly what we assumed. And this map is injective because the first group is 0. Okay, and so then you apply the previous proposition, which was kind of complicated, with a slightly simplified statement. And indeed, you get that upon restriction to all subgroups, cupping with your fundamental class or whatever you want to call it, or your Tate-Nakayama class, is going to give you an isomorphism on the Tate homology. Okay, this is basically the end of chapter 3. Let me, however, debrief you a little bit. I think I said this before quickly and didn't write it down. I think it helps. So suppose that K is a local field. What do I mean? I mean a complete discrete valuation field with finite residue fields, either a finite extension of QP or a Laurent series field over a finite field. Then I take a finite Galois extension of my local field, let G be the Galois group, let the module just be the multiplicative group of the upstairs guy. So for sure, I mean, G acts by automorphisms on L and takes 0 to 0, so preserves the non-zero elements of L. You can't argue with that. Now I claim that the hypotheses of the Tate-Nakayama lemma apply in this situation. So that's not obvious. You have to check, you have to check all these things. In particular, the most interesting thing that you have, yes, so there's several things that have to be checked here. This will turn out to be the famous Hilbert theorem 90, I think, if we do it correctly. So don't worry, we'll do that, right? That's not so deep. This one is really deep. So this one is even understanding that the group, like why is this second cohomology group equal to what it is? So this is, so we're checking that after passage to a CLP subgroup, kind of ignore that for the moment, that we're looking at the second Galois cohomology with coefficients in the multiplicative group. That is, by one definition, the Brouwer group of the field. Okay, there's another important definition, which I will at least quickly refresh you on, but the homological definition of the Brouwer group is the one that it will be useful to us in this course. And so there's a real part of local class field theory where you just compute the Brouwer group of your local field. It turns out to be surprisingly simple. The Brouwer group is going to turn out to be Q mod Z. And so that it has a very simple structure. And therefore, anyway, so the fact that this is not literally the Brouwer group. It's a certain piece of, because this is a finite extension. This is a certain relative Brouwer. It's a subgroup of the Brouwer group. Okay, so it's a subgroup of this group. It's a subgroup of a group which is a direct limit of finite cyclic groups. And so I claim, and so it's kind of plausible that it itself is a finite cyclic group, which it is. And so you have to check this. Checking this second hypothesis in the Tate-Nakayama lemma is definitely something. Once you check it, though, you get something very exciting. You get this cupping with the Tate-Nakayama class, which is understood in terms of the Brouwer group, is in particular, I mean, it's giving us lots of stuff, but in particular, it's giving us an isomorphism from the -2nd Tate cohomology with coefficients in Z to the 0th Tate cohomology with coefficients in the multiplicative group of the top field. What are both of those things? The -2nd Tate cohomology is the first group homology in general. And as we saw long ago, the first group homology with integer coefficients, as the Eilenberg-MacLean interpretation would also give you, although we did it algebraically as well, is just the abelianization of the group, also IG mod IG squared. So that's what the first thing is. And then what's this? Well, this is more clear. It is the invariance modulo of the norm map. And now this norm map is literally the field theoretic norm map product of the Galois conjugates. What did we learn? We learned that the abelianization, this was an arbitrary Galois extension, so that's even better. Maybe now imagine that it's a finite abelian Galois extension, right? Then we learned that for any finite abelian extension of our local field K, the group, the automorphism group, is isomorphic to the co-kernel of the norm map. That's a big piece of local class field theory. In particular, it is suggesting that to get the absolute abelian Galois group of the local field, I should be taking an inverse limit of all of these guys, right? Inverse limit of these finite groups. And so that suggests that the corresponding object that is going to give us the class field theory of the local field maybe should be the unit group of the field itself. Oh, I made a mistake. You guys kept nodding. There's a mistake here. What's wrong here?
Do you want to take K instead of L?
Yeah, yes, thank you. Very important, should be K. It's a bad mistake though, because the whole spirit of class, I'll just write this down. So this strongly suggests that a target group for the class field theory of K is just the, not L, because L is some variable abelian extension, is the unit group itself. What does that mean? I'll tell you what that means much sooner. It means that there should be some nice canonical isomorphism between the abelian Galois group of K and the profinite completion of this group. That's what it means to be a target group for class field theory. Okay, so if you, the whole point of class field theory is to understand abelian extensions of your field in terms of data internal to the field itself. What does internal to the field itself mean? Well, we'll take whatever you get, like it could mean different things in different scenarios. In global class field theory, it means something adelic. In local class field theory, the object of K that is internal to K is literally just the multiplicative group of K. So that's awesome. Okay, so you see that we are actually making progress here. Okay, thank you for your attention. We'll see no class on Wednesday, right? Because it's a break, and then we'll come back on Friday. I hope you guys have some more problems to solve. If there are more problems to solve, you let me know before Friday whether that's the case. And then the next lecture will be on chapter 4, which is profinite groups and their cohomology. I think that's going to seem pleasant and untechnical compared to some of the stuff that we've been doing. Okay, so see you later.
Hey,
Yeah.
I'm related to class. Did you get my email about the scheduling the defense?
Did I?
Okay, I guess I'll just send another one then. I sent it like last Wednesday.
I did, yes. Okay, I will respond to it.
All right, cool. Thanks.
All right. Did get the email. Okay, well, see you guys soon. Take care.